Alright, so what we're going to do in this video is define what it means to divide something by something else, usually referring to numbers. But we could say A divides B, A divides B, and we can shorthand that by writing A with a vertical slash. A divides B. And you find this button right above your enter button on the keyboard. If you hold down shift, that's how you access it. Um, so what this means is that B is made up of a multiple of A and something else. So let's say B is equal to A times something else. We'll call it C. So if B is equal to A times C, that means divides A divides A times C, which makes sense because A divides itself times something. It just leaves that something there. So if we divide both sides by A, these cancel out, and this just says C, which is just a true statement. So actually I'm going to keep that. So I'll put all this over here, clean this up just a little bit. So for example, we have, let's say A divides B, so let's say 5 divides 35. We'll say 5 divides 35. And that's because 35 is made up of 5 times 7. So 5 divides 5 times 7. The remainder, or the scalar value of 35 is 7 multiples of 5. Now, leave that the way it is. So, as long as B is a multiple of A, then the statement is true. If it's not true, such as 5, we could say 5 does not divide 27. Because 27 must be, in order for it to be a multiple of 5, it has to be 5 times something equals 27. And there's no solid number, there's no integer that you can multiply 5 by to get 27. And that's why this says not. It does not divide. Let's see, clear this. So how this is useful is when you're trying to compare the congruency between integers, between numbers. So basically, a congruency means, or the definition of congruency is let, I'm going to pick some arbitrary letters, let Q and R be integers, and let N be a natural number. So N can be anything. It can be 0, it could be -1, it could be +1. It can't be a fraction. That's what a natural number is. If we review what the natural numbers are real quick. Oh, I was mistaken. A natural number is 1, 2, 3, all the way up to infinity. Whole numbers, not including 0 and not negative. It's just the numbers. Integers can be 0 or negative. So that was a mistake on my part. But moving on, back to the definition of congruence. Let Q and R be integers, and let N be any natural number. 1, 2, 3. Integer can be 0 or 1 or -1, but you can say that Q is Q is congruent. Q is congruent mod n, wrong color, mod n to R. So let's store this. Let's keep this in our arsenal of knowledge. Oops. All right. And now we can use shorthand notation to write this, and it goes like Q is congruent mod n to R. Or you can write it Q is congruent to R mod n. So we just write mod out here. Parentheses. All right, and that's how you would write this in a proof. So you can keep this knowledge, and now we can use that to explain how 11 mod 2, or 11 is congruent mod 2 to 5. And this is probably some brand new notation, so we'll focus on what it means. So the congruency notation, oh, I actually forgot to finish the statement. Let Q and R be integers and let n be any number. Q is congruent mod n to R if and only if n divides a Q minus R. Q minus R. Now that completes our theorem, I guess. At least a statement. Okay, so what does it mean that 11 is congruent mod 2 to 5? Well, if you want, we can just plug these numbers directly into our formula and see if it holds true. So 11, or 2 must divide, because this is 2 and the 2 is n, so 2 must divide 11 minus 5. And if 11 minus 5 is divisible by 2, then we know the statement must be true. What's 11 minus 5? That's 6. So this is 2 divides 6. We know that's true. So basically, when you are dealing with a modulus set, which I think is the way to say it, you're counting up to a certain number. When we count 1, 2, on and on and on to infinity, we're dealing with a set that's modulus infinity. It doesn't ever stop and repeat itself. But when you count mod 2, it goes 0, 1, which is 1 digit and 2 digits, and then it starts over, 0, 1, 0, 1, 0, 1. And we use this a lot in higher up a higher level mathematics, like when dealing with series and things like that. So what this is saying is that 0, 1, well, 0 is the same as, let's see, this is 2. This is our modulus part. This is what 2 represents. Now the 11 would be somewhere along this line. Since I see we have 4, 8 here. Copy and paste. A little mustache guy. Looks like the Pringles guy. Another one. 4 Pringles guys. Alright, so 5. 5 would be somewhere along here. So 1, 2, 3, 4, 5. Actually, we'll leave this to be 0, 1, 2, 3, 4, 5. There's our 5. It's on the 1. And if we count up to 11, you'll see 5, 6, 7, 8, 9, 10, 11. And this 11 falls on a 1, as well as the 5. So since they both fall on 1s, that means they are congruent to each other. Because if you count to, if you only can count up to 1, starting with 0, then counting up to 5 in our number system is the same as just counting up to 1. And counting up to 11 in that some number system is the same as just counting up to 1 again. So that's what it means to be congruent to something. Now the simplest example is what we just spelled out here. That's when you start with the normal number line and you just differ between numbers that are, or you just group all the numbers that are even and all the numbers that are odd. You see that all of the even numbers fall on 0s and all the odd numbers fall on 1s. And we can rewrite this rule somewhat. Actually, we don't. I guess we'll keep these examples right here. But I'll keep all this off to the side as well. But I want to define what it means to be even and odd. So keep this. Now, so here's the definition of being even and odd. Let A be some integer. So let A, I'm going to make this A yellow, be some integer. Then A is even. A is even if and only if. Sorry, I didn't even write even. Yeah, I didn't write A yellow. A is even if and only if A is equal to 2 times K. A is equal to the number 2 times K. Okay. So if A is not even, then it is odd. Alright, so before I go into that, we need to define K. K is an integer. K must be a whole number, can't be half of a number. And so we can put that right into our list of assumptions. So let A and K be integers. Then A is even if and only if A is equal to 2 times K. Because if K is anything, the smallest integer is 1, then A must be equal to 2. And if A is equal to 2, then A is even. If K is equal to 2, 2 times 2 is 4, A is equal to 4, that's still even. So, but if A is not even, let's say A is odd, A is odd if and only if A is equal to 2K plus 1. A is equal to 2K plus 1. And that means, just like this, the first one will prove that some portion of the of the integer is even, and then we add 1 to make it odd. So no matter where you land, if it's an even number, moving 1 digit to the right or left, well, in this case to the right, doesn't really matter. That makes it an odd number. It does matter when we get close to 0 because 0 is not an integer. So it has to be 2k plus 1 in order for it to be defined as an odd number. And we're going to use this in a lot of proofs coming up, so it's important to understand it. I'll save all the exercises for the next video because we're already at 15 minutes, but maybe I can cut that down before posting it. Well, anyways, I'll see you in the next video.